Okay, so yeah, on Monday actually we covered all the states for the SAR register ADC's operation. Do you remember the structure of the SAR ADC? You may didn't watch the video. Did you watch the video if you were not here on Monday? That's critical because you probably won't be able to understand everything in this lecture. Just in case, let's do a quick overview for the SAR ADC. Okay, so the name of the ADC is successive approximation register ADC. For short, this is SAR. Right? And the structure looks like this. So the structure or the diagram of the entire system, you got a V-in, sample and hold circuit, and feed the signal into a comparator, and then the SAR circuit. For example, it's a 4-bit ADC. So there are 4 bits come out from the SAR, and then DAC. And the DAC has a reference voltage, which is 10 volts, for example. And the output of the DAC will be fed into the inverting terminal of the comparator. So the signal here, I just say it's comp, okay, for short. And the signal here is called VDC. Right? And MSB, so here's all the bits for the SAR's output. Let's call it B3, B2, B1, B0. Right, so that's everything about the SAR ADC. So on Monday, we had an example. For example, V-in. On Monday, V-in was 5.2 volts. For example, at one moment, the analog input was 5.2 volts. So today we're going to look at example which is lower than or smaller than 5 volts, and let's say 4.5 volts. See what's going to happen. All right, for this example. So what if V-in equals to 4.5? Again, all right. So the initial state for these 4 bits, so B3, B2, B1, B0 equals to 1000. That's the initial value of the output of the SAR, okay? Always. 1000 in the dynamic range, which is, or full scale, which is 10 volts, then 1000 will be 5 volts. Right? So this is 5 volts. So SAR is going to start with 5 volts. 5 volts here. And after the DAC, there will be an output at VDC and being compared to 4.5 volts here. Because at this very moment, the V-in right now is 4.5 volts, just 1 point, 1 analog point. And I'm trying to use a series of clock cycles to get a value which is the closest to this value based on the resolution of the ADC, and use that digital value for this analog value to represent this analog value in the system. So now if it's the 5 volts, then 5 volts will be sent to here and compare with 4.5 volts. If comp equals to 0, goes to that direction. If comp equals to 1, goes to this direction. All right, so now VDC is 5 volts, right? And the V-in is 4.5 volts. So let me know what's the value of comp? What's the value of comp? The output of the comparator. Comp for short, right? If you got 5 volts here, I have to just write it down here so I can compare. Yeah, 0, because it's amplifying the difference between these two terminals. But you say, hey, the difference is 0.5 volts. Oh, no, the difference is, what's the difference? Negative 0.5 volts for the input of the amplifier, right? And open loop gain of the comparator is 1,000,000. So you should get negative 5 million volts. But however, it's going to be clamped at 0 volts because that's the lowest potential of the circuit, right? So it's going to be saturated at 0 volts. So we're getting 0 volts. So comp equals to 0. Goes to that direction. If it goes to this direction, then you shift all the bits to the right by 1 bit and plug in the comp to the MSB. So what's going to happen is you are going to have 0, 1, 0, 0, right? So these are the bits that were shifted to the right by 1 bit. So if comp equals to 1, which is not the case, but let's take a look at it. What's going to happen? You still shift everything to the right, but you plug in 1 to the MSB. So what's going to happen is it's going to be 1, 1, 0, 0, right? So these were the bits shifted to the right just now, right? So that was not the case, so just ignore it. So what's the value here? Because this is 5 volts, so this is definitely 5 over 2. So this is 2.5 volts. And then compare again. If comp equals to 0, goes to that direction. If comp equals to 1, goes to that direction. So what's the comp in this case right now? 2.5 volts. So 2.5 volts is being fed into the inverting terminal. So what is comp right now? Five volts, right? Or 1. So we're talking about digital signals, right? 1. So we got a 1. It actually follows this track. So if it is a 1, you just plug, just keep this digit, keep this previous MSB, and just plug 1 after it. And then just keep all the other bits, keep shifting everything to the right. So you have 1, 0 left. And the LSB over here has been shifted out. So it's nowhere. Only have 1, 0 left. So now you plug in the second comp to here, right? So what is this value in analog? So this one here represents 2.5. So this one here represents 1.25. So 2.5 plus 1.25 is a pan-pan-apple pie. What is that? 3.75, right? Yeah. And here, that's not the case, but let's take a look at it. What's going to happen? So keep this 0 from the previous state and plug in 0, the current comp, to here, and then keep whatever used to be there, but shift it to the right by 1 bit. That's not the case, so ignore it. Then do it again. So 3.75 over here. What's comp? What is comp? 1? Is that 1? 0, 1, keep the previous comps still there. And plug in another one, which is the current one here. And then shift everything to the right. So what's the left over here? Shift everything to the right by 1 bit. 1. Where was the 0? Shifted out. Disappears. And what's this value here? So How to make it E there? Plus, what is this? It's 10 volts is a full range here over what? 4 bits, right? Over 16. Or 5 over 8, which is 0.625. That's one LSB. Right? So this is 0.625. And these are this. So just add these two numbers together. 4.375? Is that correct? Yeah? So that's the case, that's not the case, but let's still write down the number here. So because this comp is 0, so it's going to be 0, 1, 0. 1. Okay? $4.375. What's going to happen? What's comp? 1. Right? Still 1. So this case, right? So what's going to happen is 0, 1, 1, 1. That's the most recent comp. So still 4.375. It's not changing at all for the last two states. So what is this? What is this here? 0, 1, 1, that was the, so these were the previous comps, was reserved. So what's the LSB here? If comp is 0. I know it's not the case, but if comp is 0, what's going to happen for the LSB? Just plug in the 0 here, right? So it should be a right color 0, but that's not the case, so ignore it. Won't happen. So this will happen. So that's the final result from the ADC. How many states in total? How many states? 5 states. How many bits? 4 bits. So if you have an n bit ADC, how many states will there be? How many states are there? Yes? And the second conclusion here is the converted result is always smaller than the analog input, smaller than or equal to the voltage input. Two conclusions here. All right. Let me see anything else I want to tell you. All right, so let's summarize everything into a table. Okay. So for example, here's the number of the cycles: 0, 1, 2, 3, 4, 5, and these are the bits. And here's comp. So all these results. Let's summarize everything to one table so it looks pretty clear. Before we power everything up, everything's 0, right? Nothing. The first state, what's the first state? It's the first state for all the B's. What's the first state? Always, you're wondering how you can do that. So this is just an algorithm, right? We need this algorithm to make it work. But how to implement everything circuit into the chip, we are going to cover that later. But now just remember this is algorithm. You just need to understand the procedure of the conversion, right? It has to be 1000 at the very beginning for the first state. The first state is this. And will this state give you a comp? Is this giving you a comp? Of course. It's being fed back to the op-amp, and it's going to give you a comp. Let's call it A3. So what about here? In the second cycle, in the second state, what's going to happen in the table? If we summarize it, what's going to happen in the table? Remember, all the previous bits will be shifted to the right by how many bits? 1 bit. And then do what? Plug in the comp to the MSB. That's the second state, right? So what's going to happen here is I'm going to have A3 and 100. Is this going to give you a comp? Will this give you a comp? Of course. It's going to give you a comp in the speed of light. Available. Let's call it A2, since we don't know what is that, right? So let's just call it A2. So what's next? What's next? Yeah, shift it and then what? Plug into to where? Huh? Before or after? After what? Or before what? No, it should be after A3, right? We have been plugging everything, plugging all the other bits, all the comps sequentially after the previous one. So you're going to get A3, A2, and these ones becomes this. And this will give you another comp for free, right? What's next? Give you another comp. Oops. So the final result is just the combination of the comps. Is that clear? All right. Let's look at all the possibilities, just let you guys more familiar with all the steps. If, let's start from 100, okay? If, let's just say C equals to, which is comp, okay? C equals to 0, C equals to 1, what's next? What's here? Let's practice this one more time. I promise you this is the last time before the quiz, right? If C equals to 0, what's going to happen for the next SAR's output? If C equals to 1, then what? All right. What about here? Here. Let me know. What's this? Here. 5 bits? Oh. No, you got one here already. Here. Made it. Let me label that for you. Let's wait for 30 minutes. I'm going to go home. So easy to teach. I love to be a professor. Come on, you'll see this in the quiz, right? Is everybody getting this? People sitting behind there? Everybody? So I'm boring you. I'm not challenging you. So I'm boring you right now, right? Okay, great. Okay, got it. Um, 0, 1, plugin, 0, 1, right? Here. Never mind, I have Parkinson's disease, so I'm not doing. Yeah. So this one will be shifted out, right? So just plug in a 1 here. If you already find the tricks, you just keep counting up. 0, 1, 2, 3, 4, 5, 6, 7. 7. So next will be 8, right? Shift this out, so you're getting 1, 0, 0, 0. Shift this out, and replace it with 1 here. You're getting 1, 0, 0, 1. Shift this out, you're getting 1, 0, 1, 0. Replace it with 1, it's going to be 1, 0, 1, 1. Shift this out, you're getting 1, 1, 0, 0. And then here will be 1, 1, 0, 1. 1, 1, 1, 0, 1, 1, 1, 1. Done. That's all the possibilities. Expect this on the quiz. next Monday. All right. So the next question is how to implement this circuit, which is the fun part. Make it work. So let's just look at the table, all right? So what I want to do is I just want to shift everything to the right and plug in all the comps sequentially, and that's it. So you must think of shift register so I can shift everything to the right, okay? And also plug in something over there. How to plug in everything over there? Let's just imagine like we can plug in a 1 or a comp to there, and now after that we start thinking about the solution to that. So first, shift the register, nothing but a D flip-flop. Right? 1, 2, 3, 4, 5. And you'll see why we need a fifth one here. DQ, which is ice cream. And Durango doesn't have it, which is a shame. There are 2 more functions here. Set, reset, set, reset, set, reset. You must be wondering, how do you implement set and reset? I'm going to cover that. And clock, rising edge, okay? And for the last one, I don't need to do anything for DN clock. I just ground it. And for example, I can assign a 1 to the first D flip-flop and assign the following ones sequentially after every clock cycle. So I'm actually setting every single D flip-flop sequentially like this. But you didn't learn how to set and reset a D flip-flop. It's super simple, and you are going to do it in the homework. Let's take a look at it. How can you do that? Let's jump to the second page. No, let's do it in this page. So hopefully you still remember the structure of the D flip-flop, master-slave D flip-flop, converted from the JK flip-flop. No brainer, just keep drawing. Draw 8 NAND gates. Feedback, feed in, clock. Feed in, feedback, Q naught, feedback, clock, input. Because this is, originally it should be JK, but now it's not JK, it's D. So how to convert a JK into D? So it becomes D. Otherwise, it's going to be J and K. All right, just watch the video from the logic C241. Just watch the video if you forgot this already. But now just remember how that works. You don't need to understand how to make it work. But let's look at now we're just using that. Right? And I'm going to make this guy a rising edge D flip-flop. How can I do? What can I do? Or what should I do to make it rising edge? So D means data, right? So whatever data is here is going to be converted, will be transferred to Q, but only at the rising edge. So we need a clock. How do you want to modify the clock to make it rising edge? So falling edge will sample the data, and rising edge will send it to Q. Falling edge will sample, rising edge will send it to Q. So we want to directly make the clock connect to this clock signal input for this first stage of the D flip-flop, or you want to invert it. Yeah, because it's falling edge sample, and rising edge send it to Q. So you want the clock without being inverted. So the clock should be directly send it to the second stage clock. So that's rising edge. This rising edge trigger, right? So for example, here's the clock signal. Rising edge. So nothing should be put in here because you want the rising edge to send whatever temporarily saved over here to here. Because rising edge is going to enable these two NAND gates. But is this correct right now by far? You want to invert, yeah? Is correct? All right, so this is a rising edge. D flip-flop. So now here's the question. How can you set and reset Q? So which means I just have a little bit more control for the output, which is Q. So which means if I give a signal, I can set the D flip-flop, which means it's not being controlled by the input signal anymore. However, if I set it, Q is going to be 1, no matter what the input is, right? That means it's a set function. Set. That's a pin. That's S, right? It's not 1S. This is a pin. Let's draw a wire here. That's S, 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 S. So these are the set pins. If you give a voltage here, can be 0, can be 1. Doesn't matter. Depends on how you design your D flip-flop. It's gonna set. It's gonna set the Q. So Q will be 1. If you reset it, Q will be 0. All right. How can you make it happen? There are many ways, but let's do the simplest way. How? And I need a logic 1. I need the logic 1 to set and reset. Both are logic 1 to trigger it. Look at the gate. What are the gates? NAND gates. So what's gonna kill the NAND gates? Or if you give a 1 to the NAND gate, it's gonna happen. It won't affect it. 1 will not affect it, right? So we need a 0. Because 0 and everything will be 0. And being inverted, it's gonna be 1. So if you directly connect this pin out and make a pin available here, it's gonna be S bar. Let's make it in right. Whenever you see something bar here, which means 0 is going to trigger it. And 0 is going to trigger it. Because when S equals to 0, what's going to happen? If S is 0, what's going to happen here? If S is 0, Q will be 1. It's being set. But when S is 0, it's being set. All right. Now here, when R is 0, what's going to happen here? What's going to happen when R is 0? If R is 0, Q bar will be 1, because it's being forced to be inverted here to the latch. So Q will be 0. So when R is 0, Q is being reset. That's why when you see a bar here, I didn't draw a bar here. If I draw S bar, you know that you need a 0 or 1 to set it. If I have a S bar here, you can see this everywhere on the data sheet. If you buy a D, you can actually buy a D flip-flop, right? So they are being tipped out into a silicon die, but being fabricated into an IC. You can buy and grab from the drawer in the lab. Open the drawer, see all the cheap IC chips. It can be a D flip-flop chip, and probably has maybe four D flip-flops in there. And grab it, you can see that there are totally 5 pins available for the chip. So D, Q, Q bar, S bar, R bar. So S bar, R bar. What does that mean? Active low. So if you give a 0 to S bar, it's going to set the output. So if you probe Q, it's going to be 1. All right? So what if you give a 1 to S bar? No, it won't happen. Nothing will happen. Right? 1 is not will not affect the NAND gate. Right? So 1 will do nothing. Same story. If you give a 0 to R bar, Q becomes 0. If you give a 1 to R bar, nothing. Right? So now, this D flip-flop right here, you need a 0 to set and reset. Set and reset the D flip-flop. But now I prefer a 1 to set and reset it. How can you do it? Circuit, how do we redesign the circuit to make it happen? Yeah, just invert it. I was trying to confuse you. Don't think about that complicated. It's super simple. Just invert it. All right? Is that easy? Instead of doing this, just do this. So let's take a look at the circuit really quick and run a simulation. Do you still have your gates saved from logic class? Still have everything? Let me see. I need a D flip-flop. I think it should be this guy. So here's a D flip-flop, and it's a folding edge triggered, right? Is it? It's folding edge triggered. Okay. Anyway, let's simulate it. And there's no set and reset. So in the homework, you need to add a 3-input NAND gate to here. So it looks like this: 3-input NAND gate, 3-input NAND gate. And doesn't matter which technology you use. You can use 1 micron technology. That's what I think that's what I required in the homework. Just use a 1 micron technology. So where can I find the model file? On the website, yep. So I already provided a link to here. So see this models.zip. Just download it. Let's take a look at what's inside. So remember, I used to have a models.txt. It's the same as CMOS edu _ models.txt. You can rename it whatever you want. I used the models.txt because it's shorter, because every time I have to retype it into LSpice. But either way, so this model has the 1 micron technology, which is not fabricatable because it's just a virtual allocation package. There's no foundry can fabricate it. It's just for simulation. Okay, so this is 1 micron. I have to rename the NMOS and PMOS as N_1U or P_1U. It also has a 50 nanometer technology. It's also not fabricatable. It's just a virtual model file. It's a short channel model. We're not going to use it for all these simulations for calculation because it's not really matching calculation. So here's the model file for this guy. Or C5. C5 is 500 nanometer. It's pretty close to 1 micron. So it's predictable. It's pretty large size. If you want to use C5, which is fine, it's not going to affect anything. But you have to change the name, the model of the NMOS and PMOS to NMOS exactly. You cannot do N_1U, right? It won't work. All right, so you can use either one, but I recommend you use a 1 micron one. And for sizing, it really doesn't matter at all, as long as it's not a weird size or something. If you want to just use whatever I used here, which is fine, I just use a 10 micron for the width and 1 micron for the length, for the PMOS and NMOS. All right, doesn't matter. So that's the 3 input NAND gate, and I have 2 input NAND gates as well. So if I simulate it, and I think I want to probe D because that's the input, and also I want to probe clock because I want to see it's a falling edge trigger, and also I want to probe Q because that's the output, and also probably Q naught, so I can see it's being inverted, which means it's correct. So I need 4 clock pins. So clock on the top, or probably the second, so you can see it's being triggered. So data on the top, Q here. And now I'm going to change the range here so you can see the signal. All right. It's inverted, so great. And you want to verify the logic. Where do I want to look at? Let me know. Or what do we want to look at? As you know, this is a falling edge trigger D flip-flop, right? Only at the falling edge it's going to change the state or change the output, which is Q. Let's see. The first rising edge, you can sample the data at this point, which is 0. So it's sampled and being saved to here. They couldn't see that since I didn't probe it. And next, falling edge trigger. Send 0 to the output. So got 0. Right? Rising edge sample. Boom. So 1. Falling edge, send it to the output. Making sense? Rising edge, sample. It's a 1 here, being nicely sampled. And falling edge triggered, still 1. Sample, 0. Send, 0. Get it? Do you need more more cycles? I can keep doing this, so I can go home earlier. Or either. All right, so what you need to do is replace this guy with a 3 input NAND gate and add a set and reset. And after you run this simulation, let me show you what are these the code. What's the code? The spice code. So know what I used here. So these are the spice code. If you watch the video, you will see you can directly use the same thing here. And what you need to do is you need to change it to the rising edge triggered, right? Rising edge triggered. So you want to put the inverter somewhere else. And second, you want to replace this guy with a 3 input NAND gate and add a set and reset over there and see if that works. All right. You'll probably need multiple simulations. One simulation, verify the logic of the D flip-flop, and then set it, and the third one, reset it. See if that works. All right? Make sense? And then lay it out in electric VLSI. I'm joking. No, it's not possible just for like 5 days. You're not doing layout, right? Just simulation in LT Spice. Right? Any questions before I close it? No. Yes. All right, let's keep doing this SAR structure. See what's going to happen. So we were here. I just mentioned that every single block is one of these. And assume I can send a 1 to here, 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 here to set it. To set it, which means Q is going to be 1, right? Sequentially. Imagine I can do that. I will let you know how I do that. But now just assume you can do that. 1 clock cycle, I put this one to be 1, and all the other ones are zeros, right? So I can set this part and make it to be 1. I just do it sequentially, and then I'm going to have a comp signal from which is the output of the op-amp. Here. Try to think about the algorithm. So what the algorithm does, actually. The first time I set this one to be 1, so I'm getting a 1 here, right? A 1 here, and these all the other ones are zeros. And then what I'm going to do is I will feed this back to the clock. Keep in mind, this is a rising edge, rising edge triggered. So whenever the second one is being set to 1, it's going to give a rising edge to Q, and which is a clock for the previous one. And it's going to enable this D flip-flop and transfer comp to here. Is that making sense? What about the following ones? Just keep feeding the Q to the previous clocks. Sorry. Here. So whenever, because I know that I can sequentially offer a 1 to all these ones, 1 by 1. I set this one, and the next cycle, I won't set this one anymore. I'm gonna set this guy, and whenever I set the next one, it's gonna give a Q, a rising edge, and which is gonna trigger the previous clock, because all the D's are being shorted to comp, so the comp will be transferred to Q. It's exactly doing whatever the table is doing here. I keep shifting this one, which means I'm sequentially setting every single D flip-flop in the circuit. Set it, set it, set it, set it. Set it, set it, set it, set it. So all the Q's are the outputs. And when I'm setting the next one, it's providing a rising edge to the previous one. So it's going to accept whatever appear at comp, at the data line, and plug into the Q here as output for that register. And then for example, I'm setting this guy, so it's giving an output, and this output is directly being shorted to the clock of this stage. So it's going to plug in whatever on Q, whatever on comp to this bit. Same here. Whenever I'm setting this bit, it's going to plug in whatever here, because the rising edge is going to trigger this D flip-flop and transfer comp to Q. It's doing exactly whatever the table is doing, the algorithm is doing over here. So why do I need a fifth one? Yeah, I need a rising edge to the LSB, because eventually I still need to set this guy and plug in A1 to the previous stage. So this guy is doing this job, because this one was being sent from here, and I do not need this D to be shorted to comp, because I do not need this guy to accept any comparator's output. I just need to set it at one moment to give a rising edge to the clock of this stage, so it is able to accept whatever on this data line. So it's going to be transferred to Q. Need a rising edge here. Whenever I'm setting this guy, it's going to give a rising edge. Is that making sense? Great. So this is called a sequencer. I think it's doable. I ask you to do it in LT-Spice. It's totally doable. You can design it yourself and even lay it out. So here's a question. How can we give ones to these registers one by one? Right? We assume that we can do that, but how can we do that? We need a structure called shifter or shift register, doesn't matter, which is a more general name. So let's see. If we have the sequencer at the bottom, 1, 2, 3, 4, 5. Do we need the fifth one for the sequencer? Yes. Set, reset, set, reset, set, reset, set, reset, set, reset. D, Q, D, Q, D, Q, D, Q, D, Q. Clock, 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 clock. Ground it. Feed back to where? Feed it back to where? Clock. Not D. D or clock? Clock. So where's D shorted to? D. Comp. Until here. What's next? I need something like this. It's nothing but a D flip-flop as well. I need 5 of them. So reset, set, reset, set, reset, set, reset, set, reset, set. Also DQ, I'm not doing that right now. So the reset for the first one is being shorted to all the sets. Oh, sorry. Should be set on top. Set, reset. All right. And the Qs are being sent to set. Why does that make sense? And D is being shorted to the ground. And definitely clock is triggering all of them at the same time. So at the first clock, we give reset a 1. At the first cycle, I give it 1. So it's going to set this data, this pin here, so it's going to give a 1. But this one is going to reset all the other ones. It's going to give a 0 to all of them, which gives the first state for the SAR. And next, because you have a 1 here, I'm going to short all the Qs to the Ds. So 1 used to be here. And the next cycle, I'm going to give reset a 0 signal. And we'll release all the D flip-flops. It's not going to force this to be set anymore. So because I short the first D to the ground, so in the next cycle, this one will be shifted to here, but this will be replaced by 0 sequentially. That's how you do this. Because of this. All right, think about it after class, and probably the homework we'll do next Wednesday, though. I'm going to cover it a bit more, but you can start working on that. But, you know, there are more details I'm going to cover on Friday, right? Don't have enough time.